Today we're going to look at threaded fasteners and their torque-tension relationship. We're going to do a 4-on, 4 removal, dry torque, as well as lubricated torque and compare those values. For our demonstration, we're first going to look at a 1/2" 13 SAE J429 grade 5 bolt and corresponding nuts and washers. The grade 5 has a minimum tensile strength of 120,000 pounds per square inch, which for a 1/2" 13 corresponds to 17,000 pounds minimum tensile strength. The proof strength for the grade 5 1/2" 13 is 85,000 pounds per square inch, which corresponds to approximately 12,000 pounds of proof strength. For our demonstration, we're going to be using the installation torque of approximately 70 foot-pounds, which corresponds, based on a K value in our torque-tension relationships, of 0.18 to approximately 9,000 pounds of clamping force. We'll be reading our torque with our torque wrench here, and we're also going to be showing the clamp load on this screen, which is going to be illustrated through our load cell for our demonstration. For our first installation, we're going to do in the dry as received condition without lubricant. Our first installation torque was approximately 68.8 foot-pounds, resulting in a clamping force of 7,400 pounds. We'll now remove the bolt and simply retighten to the same torque that we initially did, approximately 70 foot-pounds. We hit a 70.4 foot-pounds, which correspond to a clamp load of approximately 5,500 pounds, which was a slight reduction from our initial 7,500 pounds that we hit the first installation. We'll remove that bolt. And do it a third installation at the same torque value, 70 foot-pounds. And once again, we drop down in clamping force. We're at a torque of about 73.2 foot-pounds and drop down to a clamp load of approximately 4,250 pounds. And we'll back that off again to our fourth installation. Now, we have not done any mechanical damage to the fastener itself. All we're doing is increasing our frictional coefficient between our mating components, the threads, the face of the nut, as well as between the washer. We'll take it to our fourth installation torque, same torque value of 70 foot-pounds, 69.1 foot-pounds, correspond to just underneath 3,000 pounds of clamping force. Stop our chart here. As you can see with our first installation at the estimated torque of 70 foot-pounds, ideally we were looking at to achieve a clamping force of about 9,000 pounds, which is what the torque-tension relationship with a K value of approximately 0.18 would achieve. We were achieved just under, or just around 7,500 pounds, just reusing that same fastener at the same torque value, that torque or the clamp load dropped down to about 5,500 pounds. And by the fourth installation, we were at 3,000 pounds of clamping force. Ideally, we're looking at 9,000 pounds of installation clamp force during all these installations. So as you can see, just by the reuse of those fasteners, all we were doing is changing our frictional coefficient, or our frictional between those corresponding members, through the zinc, through the mating components, and our clamp load dropped down significantly to well below half of that value. Now that we've seen our torque tension demonstration in the as received dry condition, which resulted in a clamping force of approximately 7,500 pounds at our installation torque of 70 foot-pounds on the first installation, and then drop down to 3,000 pounds of clamp load at that same torque by the fourth install. We're going to utilize a lubricant to try to control our K value, which then will control our clamping load. For this demonstration, we're going to use the DuPont Teflon multi-use dry wax lubricant. We're going to apply that to the threads, and we'll do the same for installation and see what we get for our clamp load. Now, with the use of the lubricant, we will have to reduce our torque value because of the lower K value. So we're going to start at approximately 55 foot-pounds and read our clamp load. Get that started. Probably a little bit on there. Down. So first installation at 53.3 foot-pounds resulted in a clamp load of approximately 8,900 pounds. Remove that. A little bit more on there. Second installation torque was 54.8 foot-pounds, resulting in approximately 9,200 pounds of clamp load. Third install at 58 foot-pounds resulted in a clamp load of 9,400 pounds. By a third installation torque, which is 55.9 foot-pounds, our final clamp load was at approximately 8,900 pounds. And as our torque charts, or as our tension load demonstration illustrates, our first clamp load was at 9,000 pounds, and at the same torque value, by our fourth install, we were approximately 9,000 pounds as well at that same torque value. By the use of the lubricant, we're controlling our frictional coefficient, which is controlling that K value, which in turn controls our clamping force. Similar with our earlier illustration, we're going to be utilizing a 4-installation, 4-removal torque-tension relationship to compare our coating for this fastener. For this illustration, we're going to be utilizing the Fastenal EcoGuard 1000-hour salt spray coating. It has built-in lubricity. With the built-in lubricity, we are going to reduce our torque value to approximately 56 foot-pounds. At 54.3 foot-pounds, our initial clamp load was approximately 9,000 pounds. And we'll reassemble for our second install. Second installation at 55.9 foot-pounds resulted in approximately 8,600 pounds of clamp load. Third install, approximately 57.5 foot-pounds, resulted again in 8,500 pounds of clamp load. And a fourth installation. Fourth install, approximately 58.1 foot-pounds, resulted in a clamp load of approximately 8,500 pounds again. As this shows, our first install, without the use of additional lubrication, had a clamp load of initially about just under 9,000 pounds, which is approximately 75% of the proof load of this fastener in ideal condition. Our second install, with a little bit of a drop. By the fourth install, we had just a slight drop down to approximately 8,400 pounds of clamping force, resulting in a much more consistent torque-tension relationship by the use of the lubricity in the coating.